Welcome back to another video on a design pattern. In this video, we are going to talk about the iterator pattern. So, the iterator pattern is all about iterating over the items in a collection, enumerating all of the items in a collection. And what is a collection? Well, a collection is a collection of things, a collection of anything, of something that you define yourself. So a bag of marbles is a collection, a pile of stones is a collection, a family tree is a collection of people, a class of students is a collection of students. I mean, anything that you can imagine we can think of as a collection. Of course, that's not true. I shouldn't say that anything can be usefully modeled as a collection, but you see my point. It's difficult to write an application without having any collections. Most applications have collections of some sort. So if you're building a game, the world at any point in time contains a collection of enemies. A magician has a collection of spells, and so forth and so forth. I mean, you can see the point. Like, tons of stuff can be thought of as collections. So let's actually draw something for that. So let's say that there's some kind of collection with some number of items within them, or within it. And the thing with iterator pattern is that what we want to say is that whenever you have a collection like this, it's one thing to iterate through them. It's one thing to say, okay, sequentially, first give me the first one, then the second one, then the third one, then the fourth one, and so forth and so forth. That's one thing. That's one responsibility. Think about single responsibility principles from the solid object-oriented design principles, the solid object-oriented design principles. If you want to know more about solid, check out the link in the description for another playlist on that. But anyways, the single responsibility principle states that a unit should only have a single reason to change. It should only have a single responsibility. And the thing is that you could say that how to iterate over something, how to enumerate something, how to traverse a structure is one thing, and whatever that structure normally does is another thing. So if you have a world in your game that contains a number of enemies, then that world has a set of responsibilities of its own, but you could also maybe iterate over the collection of enemies. You would maybe also want to be able to say, let's apply this operation for every enemy in this world. So when we say enumerate, just to make it super simple, think about the notion of running a for each loop for each enemy in the world. 1, 2, 3, 4, etc. Right? Looping over all of the things in that world. So again, what we're trying to say is that if you have some kind of collection, if I've constructed some kind of collection and it contains some items, and I want to, from the outside, from over here, right? Not from the inside, not from inside the collection, but from the outside, I want to be able to iterate, go through each of the items, right? One by one, I want to get item number 1, then item number 2, then item number 3, then item number 4, etc. Because, I mean, for any reason, I want to run each of them through some operation or check some status on them, or maybe if it's back to the game, maybe I'm giving a boost to all of the enemies, or maybe I'm moving the enemies. But, I mean, whatever. Again, like, I think you can probably imagine a bazillion scenarios or a bazillion reasons for why you would want to iterate over something. And by the way, if you now start to think about functional programming and the concept of map, let's talk about that some other time. There are some interesting sort of similarities and differences, but I could just imagine that there's a profound discussion to be had around that. So let's leave functional programming things such as map outside of this, and let's just think of it as a for each. The point here again is that if I have this collection, whenever I want to iterate through them, whenever I want to for each through them, I shouldn't have to care about the structure of this underlying collection. I built this, you built this, somebody else built this, like it was in the library, it was open source or whatever. This thing, I shouldn't have to care about how that's structured. I should be able to just simply say, give me each of the items one by one, sequentially. Furthermore, it's not just that I don't want to know about the structure of this collection. The idea is that if I can iterate over the contents of this collection with an interface that other collections also use, then I can suddenly treat different collections uniformly or transparently. So if I have this other collection and this other collection that too both contains items, then it doesn't matter if the structure of this is the same as the structure of this is the same as the structure of this, or if they're different, right? So let's say, I mean, maybe this has structure S1, this has structure S2, and this has structure S3. And sorry, now we're getting a bit fuzzy, right? So let's say that this is a list of items, so item, comma, item, comma, item, comma, item, or something like that. And this maybe actually is a tree structure. And if you think about it, a tree structure inherently, if you want to traverse a tree structure linearly, you have to decide in which order you want to traverse this tree structure. So there's this notion of in order and post order, and well, I had to Google to remember. Pre-order was the last one. Which are different ways of traversing a tree, or in other words, different ways of flattening a tree so that you can go through all of the nodes, you can iterate through all of the nodes, traverse through all of the nodes in a particular order, right? So it matters whether you go, for example, like this, here, then here, and here, then here, for example, and so forth, or whether you go this, 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 and so forth and so forth. I mean, sorry, I have a difficult time visualizing the different orders. I didn't really think that one through. But we can talk about the sort of in-order, pre-order, and post-order some other time. Anyways, the point is that there's no one true way of how you should iterate through a tree sequentially. Anyways, and this S3 might be something completely different. I mean, maybe this is some kind of absurd collection that we created ourselves. Trivially, maybe this would be like a linked list, like a node that points to a node that points to a node that points to a node, and so forth and so forth. But more interestingly, maybe this is a structure that we created ourselves. So like, I don't know, let's think about maybe it's like this object is like a two-story house that has windows on the different floors. So you can have windows here, and let's say maybe this is the door, and then windows here, and then windows here, and then one window here. I don't know why the windows are round in this house. Anyways, maybe you want to iterate through the windows of this house, and maybe this class is structured such that you have like levels. So maybe that's actually a sensible example. Like the house is sort of is like a two-dimensional array, right? Like you have the stories, and then each of the stories have a number of different windows. So maybe that's like the internal structure of the house. Like you have a list of stories, and each of the stories have a list of windows. I mean, I'm totally making something up, right? It doesn't really matter. But the point is that in our applications, we build complex structures for good reasons. And these data structures we might want to traverse. And instead of then saying that, okay, I want to be able to iterate through all of the windows for some reason, so I need to use one of these classic collections that support iteration so that I can sequentially go through them. You could do that. You could change your architecture such that, okay, let me store the windows linearly and then find out some other way of sort of making sure I know which window is on which floor. Or you could, of course, store them in this two-dimensional list, but then whenever you want to iterate through them, you flatten this list. So maybe the house class has a flatten method. So like that would be similar to the tree thing. So like the tree would do a similar thing. It would sort of do a post-order, pre-order, or in-order traversal, and then construct the list from that, and then return that list. Right? The house would do the same thing. It would sort of flatten this list, right? It would go like, okay, first let me take all of the items from this list and put it inside this grand master list. And then let me concatenate that list with all of the items from this second story. So we're sort of making this list, we're flattening this list. So we're turning this two-dimensional list into a one-dimensional list. And of course that would work, like technically that would work, but there are drawbacks with that. One of the drawbacks is that we still need a connection. So this thing that we return, this flattened list, has to be in some kind of format. So if our house is to play now nice with our tree, then the tree, the thing that the tree flattens down to, that interface has to be the same interface as the thing that the two-dimensional house flattens down to. So if this is a list, the thing we return, then this also needs to be a list. Well, you know, of course, clearly I'm exaggerating the problem because you could return something of type collection in languages such as Java or C#. But that's also a good moment for us to pause for a quick reflection. So here I'm kind of guessing, but I think this is probably correct. I guess when I talk about historical stuff, you have to be sort of take whatever I say with a grain of salt because I'm not old enough to have been into programming back in the days. But anyways, I would assume that one of the effects of the discovery of the iterator pattern is the fact that collections in, for example, Java or C# now implement the iterator pattern. what do I mean? What I mean is that if you're programming in C# or in Java, you'd probably say, well, that's obvious if I say that, well, if you have a list and an array list, you don't have to care about which concrete implementation you have. You can iterate over both of them, right? You're like, well, of course. So like if you have a list or an array list, you can iterate over both of them, and you don't have to care about which concrete implementation you have, right? Or like let's say in C# you define something as, you declare something as being of type iList, and then maybe you instantiate it as a list, but it could also be of other types. I mean, this is like standard programming. You're probably already familiar with this, and this is also the reason I'm trying to pick a different example. So most of the time when we look at iterator pattern in the literature, on the web, like most of the time when people try to explain it, they say that, well, these different collections, they would be some of these standard data structures, like maybe this is a list and this is an array list and this is a linked list. But like it took me the longest time to realize that it's not just about that, right? Because if it's just about that, it kind of seems like we've already solved this problem. It's like, okay, smart people discovered the iterator pattern, okay? Then the iterator pattern was actually implemented in Java and in C# and tons of other languages, right? So you already have the facilities of iterator pattern, which means that you now have collections that you can treat uniformly, right? Like you declare something of the base type or of the interface, and then you don't have to care about which particular iteratable thing you have. So like array lists are iterable, and lists are iterable, and bags are iterable, and hash tables are iterable, right? So we've already solved this problem. But the thing is that if you still think about iterator pattern actually still has value beyond this, because you can take iterator pattern and apply it to your own class that can have any absurd structure. It can have this like house structure, so you can have any absurd structure that you like. Benefit number one. Benefit number two, let's get back into this, right? So I'm saying like you could flatten this two-dimensional thing into a one-dimensional thing, into a one-dimensional iterable, and return that. And because we have these sort of unified collections, you could return something which is of a very general type, or you could declare that the method that flattens returns something of that very general type, and then it would be somewhat trivial for the house to play nice with the tree. Oh wait, so that actually eliminates benefit number one. So of course, sorry, scratching benefit number one. I was saying that benefit number one is that you could make iteration over your own complex structures. I forget what the word is, but like uniformly, so that you have a uniform interface with which you can traverse this tree structure and this house, and that's simply the shared sort of collection that exists in the language. But yeah, I mean, so that you can still do without iterator pattern by simply flattening the structure and returning something that is of that general list-ish or collection-ish type. But anyways, the benefit of using iterator pattern instead is twofold. On one hand, you don't even have to expose some kind of structure. So if you think about it, yes, for houses, we needed to flat the list. So like inevitably, there is some computation that needs to happen when we traverse the structure. The structure is like inherently not flat, and we want to treat it in a flat manner. So that means like inevitably there is some computation that has to go into actually flattening. But that's with the house, right? The house actually needs to perform some computation. And the tree too needs to perform some computation, because it isn't either flat. But maybe this first collection that we talked about here, maybe this thing is actually flat. And to make it, again, to think of it outside the context of like, oh, I have a list and then I have a linked list and then so you just have something here, like let's say that's I don't know, so like this is a forest class, and this forest contains a bunch of animals, and you want to iterate over all of the animals, but the animals you've just stored in a flat list. And then if we say, okay, well, the thing is we want to iterate over them, so we need to extract the list. Like these were returning lists, right? But then why would we restructure this list? We would just return the list. But the problem with this is that we are then exposing that list. So there's a benefit with iterator pattern, because with iterator pattern we're saying, I'm not going to give you the whole list at once, or sorry, the whole collection at once. What I will give you is one item. Then if you want another one, I'll give you the next item. And if you want another one, I'll give you the next item, and so forth and so forth and so forth. So that has an encapsulation benefit, an information hiding benefit. So the collection does not have to expose its underlying representation. it doesn't have to give you the underlying representation. You can simply iterate over it anyway. That was benefit number one. Benefit number two is lazy evaluation. So when I said, I give you one item and then you tell me if you want the next one, and then I'll give you the next one, and then you tell me if you want the next one, literally, that's what happens. And that means that you can stop the evaluation at any time. You can stop asking for new items. And it also means that my list can actually be infinite. So I could actually have a house that doesn't actually contain this sort of two-dimensional representation, but rather, if you just keep asking, I'll just give you windows. So like, maybe that doesn't really make any sense for the house, but let's think of it this way. So maybe there's this magician, I don't know how magicians look, but well, this dress with the stars and have a beard like Gandalf, or I don't know, like it's a magician, whatever. And anyway, so that's the magician, and then this magician maybe has like a bag of something, and then you ask this magician for stuff, and infinitely this magician just keeps giving you apples or whatever. Right? But the point is that you just keep asking for another apple and you get new apples. I just find it fascinating that we can actually produce that with the iterator pattern. So in other words, benefit number two of the iterator pattern is that you can actually construct infinite collections. And of course, then, if you would then throw your iterable collection into a for each loop, that for each loop would never terminate because it's infinite, but that's a different story. So we'll get into the definition, but let me just try to put it in one last way to make sure that we're all sort of on the same page. So think about this house here. This house has a class, and this class, or an instance of this class, contains more than just the windows, which is why I drew more parts. So maybe your class for a house, the house class, contains the door. I mean, it depends on what we're modeling here, but like, let's say material, right? So that's what we're looking at here. So what material is used for the door? Like, is it bamboo, or is it pine tree, or I don't know what we use for doors? And then the roof contains properties such as like whether it's slanted like this, or whether it's flat like that, or lots of more information about this particular house. But then another thing that it does contain are these windows. So we have this class that describes the house, and the question is then, when we want to iterate over all of the windows, or even, I mean, if we wanted to think about it more generally, we could even say iterate over all of the pieces, let's say, the pieces of the house, and let's say that all of the pieces share a common interface. So like the roof is a piece, and every window is a piece, and the door is a piece. Doesn't matter. I mean, depends on your scenario. But if you want to iterate over all of the pieces of the house, let's continue to think of it as pieces. The question is, do we say, well, I ask you to maybe like get all pieces. And what's the response to that? Well, maybe that's something of type list, or sorry, I list of piece, or something like that, right? Or probably even more generally, like an I collection of piece. So you get back some kind of list of pieces. So back to the two benefits then. This, conversely, has the two drawbacks. So this means that we can't model infinite houses, because we need to return a concrete collection, and a concrete collection needs to be finite. Again, this is now not actually true if we would return an I collection, because if we're thinking about this in terms of C#, C# actually does implement the iterator pattern, so you could then construct an infinite collection and return that infinite collection, but let's not think about that now. But anyways, drawback number two, in other words, the opposite of benefit number two, is that you now have to, well, sorry, I'm not sure if I now messed up the order of 1 and 2. Anyways, one of the benefits that we mentioned were that you don't have to expose the actual underlying collection. But in this case, we actually do that. Yes, in this case, in the case of the house, the list is probably produced whenever we ask for get all pieces, and then we return that. But if we cache it, for example, then we'll let out the same instance, the reference to the same instance multiple times if other pieces of the code ask for get all pieces. And again, if we're in this case, if we're in the case where we actually have a list, it would be pretty strange of us not to return that list. I mean, intuitively, we would just probably return that list rather than copy the whole list, like iterate through the list to produce a copy of the list and then return that copy. The thing I'm trying to point to is that the danger when we're in languages that can actually mutate the contents of a list is that we pass this list by, or this collection by reference, which means that if we pass it out of this, right, if we have this, so I don't know what this would be, what did we say? This was the forest, right? If we have the forest and then we pass out this collection out when we call get all pieces on the forest, we get, or of a forest instance, we get all the pieces back, and then we have a list of all of the items. And that list isn't actually a new list. It's actually the same list that's in this forest instance, which means that if we start to like push new things into this and extract other, like remove other things from it, suddenly we're changing the contents of the forest instance, probably inadvertently. And even if it's not inadvertently, don't do it. I won't drag you through that discussion again, but like see the composite pattern video for a bit more about the discussion of mutation. But whenever you can reduce mutation, or whenever you can avoid mutation, avoid mutation. And this is just a dangerous scenario when we're passing out the reference to that list, because suddenly people might actually mutate that list. Anyways, let's move forward. Or wait, I just remembered a third benefit. Sorry, this we really have to talk about. The third benefit is that you can keep track of where you are in the iteration, pause at that location, and then continue later on. Now clearly you can do this with for each loops and for loops by just keeping an index, but it's much more simple when you use the iterator pattern. So what I mean is that, say that when we are iterating through the pieces, let me change the color here. When we are iterating through the pieces of the house, maybe we first get this, then we get this. So in other words, first a window, then a door, then this window, then this window, then this window, then this window, then this piece of the roof, and then this piece of the roof. For some reason, I mean, it doesn't matter which order this is. But we get all of those pieces. So the thing is, when we use iterator pattern, we're going to have a pointer that points to whichever item we're at now. So when you said, give me the next item, I'll give you this, shoop, and then I'll say, okay, now I'm here. Then you say, give me the next item. I'll give you the 2, choop, and then I'll change my pointer or move my pointer to number 3 here. So that if you ask me again, give me the next item, I'll give you this window, shoop, and then I'll move my pointer to number 4. So the iterator pattern is not only about, we didn't actually talk about this, but the iterator pattern is not only about being able to, let me show this. It's not only about being able to say house, let me just call it H, equals a new house. Let's assume that by default it has a number of pieces, so that I don't have to specify them. But clearly, probably you would pass them through the constructor or something like that. But the iterator pattern is then not only about being able to say for each piece P in, and then open that up, and then do some stuff, and then close it. Right? So this is iteration, right? When in languages such as C# or in Java, they call these different things, but we have like iCollection, but then we also have IEnumerable and IEnumerator. So if house is enumerable and has a method that returns an enumerator in C# and there's an equivalent idea in Java, that means that we can use this for each construct even though it's not a collection. So we can say for each piece P in H. And this is essentially because of iterator pattern. And this is why I was saying that, back to the idea that if we don't talk about more complex structures, it might feel completely silly to talk about why we would need the iterator pattern, because we already have this unified interface. Like if you have a linked list and a list in C#, they are both enumerable, so you can still for each over both of them without having to think about that, oh, this is a linked list, so I have to do such and such, and this is a list, so I have to do such and such. Now, clearly that works because of the iterator pattern, but even beyond that, iterator pattern is still useful. So anyways, by making the house enumerable, we can then do a for each over it. Now, this is in some sense then syntactic sugar within that language that gives us the capability of using the for each keyword. What actually happens, what happens sort of under the hood or in a less sugared manner, is that if we didn't have this nicety where we could use the for each construct, what we had to do is we had to do this. We had to extract the iterator. Again, we'll get into this in more detail, but we would have to extract an iterator. So we would say, okay, iterator is the type, let me call it I, equals h.getIterator. So the age is a house, and we're asking the house for its iterator, and it will return an iterator. So it has this method because, we'll get into this when we look at the UML, but it has this method because it is enumerable. It is an aggregate. It is an iterable. So it's the responsibility of something which is iterable or enumerable or an aggregate. It is the responsibility of that thing to be able to return an iterator. It's the responsibility of that thing to have a method called getIterator that returns an iterator. And when we get back this iterator, what can we do? Well, on this iterator, we can, for example, use this iterator in a while loop. So we can say while I dot has next. Returns a boolean, right? True or false. So we'll while. And then in this while loop, what do? We say I dot next, and then I dot current item. And then let's close this while loop. And now this is not doing anything useful, but it's for purely illustrative purposes. And what's interesting about this portion, about the while loop, is that we're doing exactly what I tried to exemplify when I said, okay, you ask me for the next item, I'll move my pointer and give you the next item. Actually, maybe I moved the pointer before, but it probably makes more sense to do it this way. There are different versions, right? Either I move the pointer whenever you ask me for an item, so I'll give you the current item and move the pointer, but that doesn't give you the possibility to ask me for the same item multiple times. So I actually think this makes more sense rather than what I said before. So what happens is, you say, has next, you ask me, do you have another item? I say, well, yes, true, I do have another item. Okay, then you say, okay, move your pointer to that item. Choop, I moved my pointer to the next item, and then you ask me for that item, and I'll give you the current item. And we continue to do this in the while loop. And then you ask me, okay, do you have another item? Well, yes, I do have another item. I'll move my pointer, and then I'll give you the current item, right? And then we just keep on doing this. And that was the problem with the wizard, right, that we talked about before. Like if has next is essentially always, literally always true for me, clearly this loop will never exit. But I mean, you could do it, and it's an interesting thought. And there are probably many scenarios where it might actually be useful. So if you think about it, I mean, you could create a sequence of some kind of mathematical operation that gives you so like you could create a sequence of Fibonacci, and it's lazily evaluated, which means that the Fibonacci sequence by definition is infinite. Like it has an infinite number of numbers, because you can just keep on saying, okay, but what's the next Fibonacci? But what's the next Fibonacci? And then of course maybe it doesn't make sense in this context, but that's simply a usage problem. You should then use it in a different way. But yeah, let's not dig too much into this infinite stuff. Anyways, and again, when we do current item here, we get back the item that the house, let's say, for example, is currently pointing to. So if we've said next 2 times, then we've moved from this to this to this, so we're at number 3. So current item will return number 3. And if we don't next again, but we just simply ask for current item multiple times, we'll get 3 back. And this is what I was trying to get at when I was saying, wait, okay, actually there's benefit number 3. So benefit number 3 is that you can remember the location. So think of it this way. What if you have an inventory? So you're building a game and you have this inventory. So maybe not the infinite wizard, but let's remove this stuff. But if you have this dude in the game, and this dude has an inventory of things, or let's say that there's this spinner. By the way, there's this super interesting playlist on YouTube where somebody gives examples of design patterns with examples from games, like actual screen captures of games, and then argues that this is very much like Iterator Pattern, or very much like composite pattern, or whatever. I'll link that in the description. And I think they do something very similar to this. But like, let's say that you have like a spinner, let's say on screen, right? Like you have your hero on the screen, and then in the bottom right corner or whatever, you have the spinner where you can switch between, like, okay, here you have a sword, it's not a beautiful sword, here you have an apple, and here you have a key, and here you have a hat. Because I don't know, I mean, I'm trying to stay non-violent, and then it's super tricky to come up with anything useful. Anyways, so we have this spinner, and the spinner points towards which item you are currently at. So when you ask for the next, maybe you just move the spinner boop, to this, and then to this, and then to this, and then to this, and then to this, and to this. And now we're suggesting that it would be infinite, right? So maybe to make it non-infinite, maybe the structure is this. So you have these 4 items, but you have this pointer that points to which item you are at currently. And then you press next to move to the next, and then you move here. And then maybe this is an iterator that has next and previous. So then you move here, and then you move here, and then you move here. And then if you try to go next again, you can't, because then you're at the edge. So then has next would return false. But then you could say previous to go backwards. So that would be a way of switching between the different things in the inventory of the hero. And you have memory quotation marks. So you know which item you're at. So you could always ask for the current item, and you could trivially move between the items. I mean, that's one way of thinking about potentially using the iterator pattern. Instead of, again, trying to think of an alternative. What would the alternative be? Like extracting the list, having an index, and then incrementing the index, and then taking out the next item, and then saving that item as like the current item, and saving the index. I mean, under the hood, this is what the iterator will do. This is what the iterator pattern will do. It's just that we're doing it in an encapsulated manner. We're doing it in a specific place. We're saying that, wait, this thing is iterator specific. This is about enumeration. So you shouldn't have to take this logic and scatter it in your code. It shouldn't be part of the hero. It should be part of iterating over this collection of things. Or it shouldn't be part of the inventory of the hero. It should be a part of an iterator that aims to iterate over this collection within the inventory. But anyways, I think that's probably way too much talking without actually reading the definition. I don't know really how we ended up here. So let's now look at the definition of this pattern. And let me also just mention that if you're not familiar with this playlist, what we're doing in this playlist is that we're walking through design patterns one by one for object-oriented languages. So if you're not already subscribed, now is a super good time to subscribe. And if you think this video is useful or any of the other videos, please feel absolutely free to share this video with anyone you think might appreciate it. Massively appreciated from my side. But anyway, let's now get into the definition. So I'll read you the definition from this book. Design patterns, elements of reusable object-oriented software. And again, about side notes. This book and this book, Head First Design Patterns, are both excellent books if you want to learn more about design patterns. Clearly, I try to cover a lot in these videos, but there's so much stuff in these books that's not covered in these videos. Head First, for example, talk a lot about design principles. So like when I said that, oh, okay, this is like the single responsibility principle. Head First actually contains a lot of stuff on that. So like, well, this is an instance of the open-closed principle because this, and this is an instance of single responsibility because this and that. So that alone makes this book super useful. And the design patterns book, Elements of Reusable Object-Oriented Software, I mean, firstly, this is the classic book, a gang of 4, because there are 4 authors, and this is the book that sort of put the notion of design patterns on the map, or gave these things the names that they now have, or that we now use, I guess. So in my mind, I think it's useful to go back to the source whenever I have doubts about whether we are misunderstanding or misinterpreting the patterns, and essentially look at what the original intention was. So for example, abstract factory pattern is often, in my humble opinion, misexplained, and then it's super good to go back to this book and say, okay, what was their original intent? Now clearly, of course, I mean, we might still disagree with what they are suggesting in both of these books, of course, but still, I mean, there's a difference between disagreeing with what they suggest that we should do and misquoting them, right? Saying that they meant one thing when in fact they meant another thing. And don't feel discouraged by the thickness of these books. I probably still haven't read every single word in these books, right? I sort of use them as reference book, where the Head First book for sure is a bit easier to read sort of leaf to leaf because it has a lot more narrative, while Gang of Four's Design Patterns book is more like a reference book because it's more like, here's this pattern, this is why you would use it, here's the definition, here are some code examples, and this is how it relates to other patterns. Next. And so forth. But still, I mean, as oftentimes with technical books, my humble opinion is feel no pressure to sort of read them leaf to leaf, read a bit here and there and jump if you want to. But anyways, now I'm babbling too much. Super good books, links are in the description. So let me read you the definition from Design Patterns, Elements of Reusable Object-Oriented Software. The iterator pattern provides a way to access the elements of an aggregate object sequentially without exposing its underlying representation. And so hopefully this kind of sounds like what we talked about before. The iterator pattern gives us a way to access the elements of an aggregate object. In other words, an object that aggregates a number of things, that contains a number of things. So like we said that the forest could contain animals, and a tree contains people. Let's say this is a family tree. A family tree contains people, and the house contains pieces, and the wizard contains apples. Well, contains was a bit funny word in that sense, but has apples, aggregates apples. And what we want to do, the end goal here, is to access them sequentially. One, and then the next one, and then the next one, and then the next one. But we want to do so without exposing the underlying representation. And if we rephrase it, I think about it as without needing to care about the underlying representation, without having to care about how this collection is actually structured, right? How this forest chooses to structure this collection of animals, or this family tree chooses to structure the people. Of course, here it was silly because if it's a tree, it's probably a tree, but the house could have multiple different representations. So when we iterate through them sequentially, we don't want to have to care about the structure. And that's the definition. So let me put this book aside and let's look at the UML. So we've got 4 things that we need to care about. What are these? Firstly, we've got an iterable, also known as an enumerable or an aggregate. It's the thing that aggregates other things. It's the thing that contains things. It's the collection, essentially. So the house or the forest. We have an iterable, then we have a concrete iterable, and then the concrete iterable is an iterable or implements the interface iterable. And that's one inheritance hierarchy. The second inheritance hierarchy is that we have an iterator, which is implemented by or inherited from, or rather, there's a thing that inherits from the iterator. And that thing we simply call a concrete iterator. So in C#, for example, their version of iterable is enumerable, and then iterator is enumerator. So the thing that can be enumerated and the thing that does the enumeration. And then we don't have these concretions, but then you build the concretions and inherit from these, and then say that you implement these interfaces. But if you would build your own thing, right? If you would implement Iterator Pattern for your own house or for whatever, then you would probably give iterable a sensible name, iterator a sensible name, and the 2 concretions, which of course can be multiple ones. Let's actually do that at once. Let's use this notation again to emphasize that probably you're in a scenario that where you have multiple ones. So again, I'm drawing this as usual sort of leaf-on-leaf notation instead of adding multiple realizations of this interface. And then same thing for the concrete iterator. There might be multiple concrete iterators. So again, like multiple realizations or multiple implementors, essentially. But let's get back to this thing. So these are the sort of 4 key things that we need to care about. Now, oftentimes when we draw these UML diagrams for patterns, there's this thing called a client that we use just to emphasize that, okay, whenever we're using this code, which piece are we actually using? So in this case, the client would be using the iterable and the client would be using the iterator. So remember, this arrow is has-a rather than is-a or implements. So if you think about what we wrote down here before, when we said we instantiated the house and then we asked the house instance for its iterator, and then we asked the iterator for whether it has next, and then we nexted it, and then we got out the current item. That is why why the client has both of these. So the client has an iterable because that's the house. The house would be down here. And then we ask it for its iterator, and then we suddenly have an iterator, and that's why we have an iterator. But this always depends a bit on your scenario. So let's remove that so we can think more about the iterator, the iterable and the iterator instead. So what methods does the iterable require? If you are an iterable, if you claim to be iterable, then you need to implement get iterator. Actually, let me put the return type as well. So you need to implement a method that returns an iterator and is called get iterator. Takes no arguments. Which then of course means that the concrete iterators also have to have a method that returns an iterator and is called get iterator. And I said of course, but I mean the point of the concrete iterables specifying a method called get iterator, sorry I get a bit confused about the iterable and iterator, like you have to really stay focused and not get them confused. But the concrete iterable has a method called get iterator, even though its parent has one. So, I mean, if the iterable was an abstract class or a superclass, then we could supply a baseline implementation for the getIterator method, which means that the concrete iterable maybe didn't have to have one. But in most of the scenarios, I assume, maybe not literally most, but in most of the scenarios I assume the concrete iterable actually needs to define its own method for the iterator. Because the point is, the reason we use the iterator pattern is, amongst others, that our concrete iterables have different structures of their underlying collections. Or in other words, this first concrete iterable might be the house, the second one might be the tree, the third one might be the forest, and so forth. So we have different complex objects that we've built that have different structures, and we want to be able to iterate over all of them uniformly. But the thing is that if you have a house, you need to iterate over it in some manner. And if you have a tree, you need to iterate over it in a different manner. And that's what we're going to use the iterator for. So we're going to have to return different iterators depending on which type we are in, which type of concrete iterable, which subtype of an iterable we are in. So this is why we can't just have it up here in the iterable, but we specify it up here because we say that to be iterable, you necessarily must define this method. So the reason that we specify the getIterator method up here in the iterable is that we want to be able to treat all of these concrete iterables uniformly. I mean, if you think about it, think about the code example that we wrote down here before. And then we had something like iterator I equals concrete iterable, which in the previous example was h, the variable name was h because it was of type house. So concrete iterable dot get iterator. So we declare a variable of type iterator called I, and into it we store what's being returned from calling the method getIterator on a concrete iterable. And again, this concrete iterable is of type iterable. So this concrete iterable is of the iterable type, and the point is that we want to be able to treat all of the different iterable things uniformly. So we had a house and a tree and a forest, whatever. I mean, a list or whatever. We have these different collections and we want to be able to treat these collections uniformly. So I mean, concretely, we could have had, instead of concrete iterable, we could have had forest.getIterator, but we could also have had family tree.getIterator. And again, I mean, these are just variable names, but I'm changing the variable name to emphasize that the type would be different. More specifically, the subtype would be different. So these can all be treated interchangeably. And that's one inheritance hierarchy over here, or polymorphic hierarchy. And then we have another one over here. And that's because when we call getIterator, we get back an iterator, and that's the unified interface here. That's the parent class here. In this case, most likely an interface rather than a class, but an interface iterator. So all of these concrete iterators inherit from or implement the interface iterator so that we can treat them uniformly. So if you think about it, when we call the method getIterator here, this method, the code that will actually be executed is the code for getIterator in one of these concrete iterable classes. If we just talk about iterables, we don't know which one. But polymorphism, at this point in the code, we will happen to have a concrete one. I mean, this is an interface. We can't have an instance of this. We need to have an instance of one of the concrete iterables. And if they all have different implementations for the getIterator method, we will call one of these implementations. But all of these implementations all return iterators. They all return an iterator. So when we call this method, we will get back an iterator that we can store in the variable I here. And this iterator, same principle, the second polymorphic hierarchy, the second inheritance hierarchy, this iterator that we get back will be one of the concrete iterators. So actually, this is an instance of the factory method pattern. So getIterator here is a factory method. So in some sense, an iterable is a factory that constructs iterators. And of course, I'm not just making that up. I mean, I think both of these books actually talk about it. So if you want to know more about that, dig into these books or see the videos on factory pattern, of course. But anyways, so we get back a concrete iterator, but masked as or behaving as an iterator, behaving as its parent interface. Okay. We haven't specified methods here in the iterator and the concrete iterator. So let's look at that. So to be an iterator, you need at least 3 things. And actually, we've seen them before. The 3 things that we need are a method that returns a bool and is called hasNext. In other words, we need to be able to know whether this iterator has iterated over the iterable all the way to the bottom or all the way to the end, whether it has iterated through all of the items, whether we've seen all of the items already. And and it needs to have a void method. In other words, a method that doesn't return anything, but that actually mutates the state of the iterator, which we call next. And by the way, I mean, I've talked about this in other videos, but clearly, whenever you have a method that mutates something, you could also redesign it as an immutable version of that method. So instead of having a void method that's called next, we could have a method that returns an iterator, in other words, something of the same type as this is, that's called next. So the iterator could return a new version of itself or a new instance of itself with the pointer moved to the correct location. That would be a way of avoiding mutation within this iterator. But that's a very general statement and can essentially be applied almost anywhere where you have mutation. So almost anywhere where you have a method that changes the state of an instance. Instead of changing the state of an instance, you could duplicate the instance and make the copy contain the new information. Or in other words, make a copy containing the new state, which is the state you wanted to change to. But anyways, that's a completely different discussion. Let's now stick to mutation just to keep things simple. So we have this method that returns nothing but moves the pointer to the next element. And then we have a method that returns the item. So let's just call it current. So maybe I should say current item. We said current item before, but let's just say current to save space. And the question is what this returns. That completely depends on your scenario. So you could do things such as specify that it returns object, say, and that means that you could return just about anything from this iterator, and then when you get it back, you would have to downcast it to whatever you wanted to use it with. Or you could do some kind of generics thing. So you could say this is an iterator over t, such that when I call current, I'll get back something of type t. But of course, then we would have to use this t earlier on as well, because since this iterator is created by a concrete iterable, then this concrete iterable must be of a t. So I mean, we need this t all over. Then we would have to say that, okay, this iterable is an iterable over t's, such that when we call the getIterator method, that will return something of type t and so forth, and we need to use the t here as well. But I mean, let's not do this now. Hopefully, I mean, if you're familiar with generics, you can probably somewhat trivially figure out how you can use t instead. So you say you have an iterable of some t, and then you have concrete iterables also over t, and then you use that same t when you specify the getIterator method, such that when you get back an iterator, you don't just get back any iterator, you get back an iterator of t or over t, depending on how you want to express this, such that this iterator then iterates over things of this type t. Completely doable, but I guess let's talk about that some other time. And also, if you're interested in that, ping me in the comments, and then maybe we can make a specific video on how to potentially generalize the iterator pattern. But for now, let's stick to concrete types. So I'll remove these t's, and then we will simply assume that we have a thing called item. So in other words, what we are looking for in this whole scenario is items. So in other words, iterable is an iterable collection of items. It's an aggregate of items. It's an enumerable collection of items. It's something that contains a bunch of items. And literally then we call the type item. And then, of course, in these concrete iterators, we then need to have implementations for these methods. So the same methods, so bool has next, void next, and item. Sorry for writing a bit sloppily, but it's really literally the same stuff as here. So these would be the concretions. These would be the actual implementations of these methods. So again, this would probably be an interface, and then the concrete iterators would have to specify how they will actually implement these methods. And let me say two things. Firstly, we separated current next and has next into three methods. You could merge them so that you only have two methods, and you could even merge all of them so that you only have one method. We mentioned before that you could merge, I can't remember which one I mentioned before, but I mentioned that you could either merge next with has next or with current, so that whenever you ask whether there is another one, you would also push forward the pointer or progress the pointer. Or in the other direction, you could think of it as whenever you say current, whenever you pick out the current object that we're pointing to, you also move the pointer forward. And those are ways of getting down to two methods. But you could also, of course, do all of these things in one method. I mean, and if I'm not mistaken, I think this book actually talks a bit about it, like Like they exemplify how you could, for example, return a default value or something like that if there are no more elements. And then you would simply just need one method that you call that progresses the pointer, returns the value, or returns the value representing that you don't have any more values. But time for another side note. There's this thing called command query separation. I think it was originally introduced by Bertrand Meyer, who is the inventor of the programming language Eiffel. And it states that you should separate methods that perform queries from methods that execute commands. And essentially, this just means that you have to choose. Either you have a method that doesn't change anything, or you have a method that changes something. But you can think of these as queries, as database queries. Either your database query is actually a query, is actually asking something, right? It's trying to get some data back, like give me all of the users with invalid email addresses. Give me the first names of all of the users, etc., etc. Or you run a query which actually updates something, which actually changes the contents of the database. So insert new user with the following details. Delete this user. On this end, we mutate, we change the contents of the database. We change the state, or I should say the state of the database. And in this other world, we don't change the state, we just simply ask questions. And it's really powerful, in my humble subjective opinion, to separate these two. And by the way, I have another video about the command query separation, so check out the link in the description for that video. And so if you strictly follow command query separation, it kind of helps you to maintain sanity, because then if you have a query, you can be certain that this query will not later down the line turn into a command, because you were actually following command query separation. Whereas if you didn't follow that, you might call something that looks like a query, but which ends up changing the contents of the application. So just think about that, right? What if you assume that the method hasNext is a question, right? Because it actually sounds very much like a question. But if hasNext also changes the iterator, you say, do you have another element? And then it answers you. But under the hood, it actually progresses the pointer. How would we know, right? It's called hasNext. It sounds like a question, and then it actually does something as well. That's super confusing. So then the next time you call hasNext, suddenly you don't, and you're like, but you just said I have another element, and now you're saying I don't. Well, it's like, makes no sense, right? People have varying opinions about this. Again, check out the other video. Clearly, just the notion of popping on a stack, for example, is also then a violation of command query separation. But anyways, I think it's a good idea with command query separation, so this is why I opted for making them 3 methods, and not 1 and not 2. So we are missing one arrow, and that arrow is that the concrete iterables will construct concrete iterators. And in the Gang of 4 book, they actually use this dashed arrow to denote that these construct these. But let me just tell you, I mean, that's what we're trying to denote here, that concrete iterables produce concrete iterators. And because we have this situation where a concrete iterable, any particular concrete iterable, will produce a particular concrete iterator, then it's a relationship between a concrete iterable and a concrete iterator, and not a relationship between an abstract iterable and an abstract iterator. So in other words, given any particular concrete iterable, it's not that it produces iterators, it produces some particular concrete iterator. Now surely you might create your own inheritance hierarchy downwards from this concrete iterator, because you might want to have multiple types of the same concrete iterator, but just think about that, because there are some interesting avenues down that path as well. But either way, iterables produce iterators, and that's why we have this method called getIterator. But in the Gang of 4 book, and on Wikipedia, but not in the Head First book, they draw an arrow in the opposite direction. So, and this discrepancy, I guess, stems from that this depends on how you actually implement this pattern. But when they do draw this arrow pointing from a concrete iterator to a concrete iterable, I assume that what they mean is that since the iterator is iterating over an iterable, so all these iterators, since the spinner spins over something spinnable, since the traverser traverses over something traversable, then this traverser, or rather iterator, needs to have a reference to the thing that it is traversing, the thing that it is iterating over. In other words, the iterable, the thing that affords iteration. And so that's why we have this arrow. But this isn't necessarily always the case. I mean, what will happen if we have this arrow is that when the concrete iterable instantiates a concrete iterator, just think about it, we will say new, let me say C iterator, C iter for concrete iterator. Through that constructor, we will then pass this. Right? It will pass itself if we have this relationship. So the concrete iterable constructs a concrete iterator and passes itself, so that the concrete iterator will have a reference back to the thing that it's supposed to iterate over. Because otherwise, how would it iterate over it? But that's not the only way. I mean, for example, we might have a concrete iterable that doesn't really expose a lot of stuff using public access source. Like, let's say if we have the house, for example, maybe we have no way of, from the outside, accessing all the properties of the house. So then maybe the concrete iterable either sends the concrete iterator something it can iterate over, or sends all the pieces to the concrete iterator. So that means that concrete iterators can actually be extremely specialized because they don't get access to some particular iterable, but rather to the contents of that. So I mean, let's just think about a very simple example. If you have the forest, for example, we said the forest uses a list. So if we have the forest and then we have a pond, for example, and these are two different things, but both of them make use of lists, then maybe we don't have to write a pond iterator and a forest iterator. Maybe we can just simply write a list iterator. And so when the concrete iterable then creates the concrete iterator, instead of creating a pond iterator and a forest iterator, it then simply creates a list iterator and takes the list from this concrete iterable, from the forest or from the pond, and passes it to that list iterator. Then this wouldn't have a reference to the concrete iterable, it would have a reference to an internal of the concrete iterable. But you know, I mean, pros and cons. And for this moment, let's stick to this dual relationship where the concrete iterable instantiates a concrete iterator and passes itself to the concrete iterator so that it has a reference back to the thing it's supposed to iterate over. Let's move on. So that's essentially the UML diagram. Let's try to make this a bit more concrete by talking about a specific example. Think about gaming. So let's say that we are building some kind of game where you have players that have inventories. So if I'm a player in the game, I can have an inventory. And let's say that I can have a hand inventory or a hand-based inventory, which essentially means that I can carry something in this hand and I can carry something in this hand, right? We're not trying to model reality. We're modeling a game, right? So like in this world, there are all of these different game items, right? Like there are valuables like gems and like money and like Bitcoin, but also there's food like apples and fruits and vegetables and berries and whatnot. I mean, there are a bunch of different things, and you can only hold one thing in your right hand and you can only hold one thing in your left hand if you have an inventory that is hand-based. But then you can have other inventories. So let's say you could have a backpack inventory. And this backpack inventory might work completely differently. So maybe that's limited by, let's say, the weight of the items, which means that if you have very small items, you can carry tons of them. But if you have very large items or very heavy items, you can only carry very few of them. So the number of items that we can have in a backpack inventory is not necessarily depends on the weight of the items. And then maybe there are other absurd stuff. Think about the infinite list stuff again, right? Maybe there is a like a magic inventory that it doesn't matter what you put in this inventory, it always turns into apples, and then whenever you try to extract things from this inventory, you always get apples. I don't know. And so you can probably see how I'm trying to say that you have these things that have different structures. Like you would build the hand inventory in a different way than you would build the backpack inventory, for good reasons, right? I mean, it doesn't make any sense to build the hand inventory in the same way as the backpack inventory, because the backpack was concerned about weight and like it could have a very large number of items, whereas the hand inventory was just like you have something on the left and you have something on the right. It's like, if you think about the composite pattern video, in the composite pattern video we talked about trees. So if you have a binary tree, it's completely unnecessary to construct nodes that have lists instead of a left and a right attribute. So if you're constructing a binary tree, you know that you can only have one item and another item. And if you then use a list to manage that collection, that means you suddenly are prone to a sea of errors that you have to make sure that you don't hit. So like a list can contain a lot more items. So what happens if you accidentally, or if a coworker on your programming team starts to add things to that list, not realizing that you're trying to model a binary tree? So I'm trying to figure out a better way to put this, but something I'm thinking about these days is that I think it's appropriate to use the smallest, quotation marks, smallest data structure that you can for a given problem. So like, don't use something which is more flexible than you need, right? Don't use something that can contain more than you need. If you need something that is very specific, when you get to the level of concretions, right? When you're at the level of abstractions, that's fine. But when you get to the level of concretions, use something which is tight around that fits tightly around your requirements, so that you don't use something which is intended for a much broader usage, because that gives you a lot of potential errors that you have to protect for or protect against. But anyways, another side note. So back to the point. The point then is that if you have this hand-based inventory and then you have a backpack inventory, then for good reasons you might choose completely different representations. So again, like if you've come across examples of the iterator pattern before, they often talk about like how one piece of the application wants to use a linked list and how another piece of the application wants to use a different data structure, and people refuse to change. And I mean, that's just ridiculous. You might actually have very good reasons for using different data structures. Even if you think about it this way, if you think about hash tables, for example, you might have a class that for requirements reasons need to have very quick lookup. So then you might actually appropriately use a hash table. It's not about like, oh, you want to use a hash table rather than this other thing, and now you need a hash table to play nicely with the list. It's more like this class that you have here needs to use this data structure because that's the most appropriate data structure for that problem. But then this other class over here needs to use another collection-like data structure because that's the most appropriate data structure for that scenario. Okay, and so in our game example here, that's why we would want to use the iterator pattern. So let's map our game example to this UML that we have on the board now. So instead of having an iterable, let's think about what we have. We actually have, so these are the things that contain things. So the collections, and these are now the inventories. So inventory. And then of course, these probably do other things that belong to our application, right? But the inventories can also produce iterators. That's the responsibility. Like the notion of being an inventory is that yes, you may want to do a bunch of specific things that's inventory specific, but if you are an inventory, you need to be able to allow outsiders to access one of the items at a time. You need to supply users of you, the inventory, with the capacity to iterate over your items one by one. Because like for a bazillion different reasons, we might want or need to get access to these different elements within the inventory, or let's say the items within the inventory. I mean, if nothing else, let's just say that we want to be able to display them on screen. Or actually, much more sensibly, let's put it this way. Again, like we were drawing with the inventory selector or the item selector. Like you have the character on screen, and then you press next, and you flip that sort of the dial. You flip the selector of like which inventory item you have active. Or even like that, maybe you press a menu button, you bring up the whole inventory. So then first you need to show the whole collection. So like you need to iterate over them in order to be able to display all of them. But then you need that pointer to be able to say that, oh, I'm pointing at this particular one right now. And then maybe, if you think about it that way, maybe we have a handheld inventory and a backpack inventory, and we need then to be able to display both of these on the same screen. So then you'd first iterate through the hand collection and then the backpack collection, or something like that. So this is then the inventory. And next, that means that these are concrete inventories. But if we actually think about our scenario, then this first one, again, could be handheld inventory. And then the next one would then maybe be the backpack inventory. And again, maybe we'd have that magic inventory, or maybe more sensibly, maybe we could have like a home inventory. So you know how in some games, like you have the home base where you can store a bunch of stuff, but then you can only carry some stuff with you. So maybe that's what we're modeling here, like the handheld inventory and the backpack inventory is what you can carry with you. Like, and then the home inventory is stuff that you can, again, move into the hands or move into the backpack. I mean, just hypothetically, we're just thinking of something that could be plausible. So what would then happen on this side? Well, these we should probably call not just iterators, but inventory iterators. And again, this is back to the reason that, like, if we built this using generics, if we built this using the notion of T, then maybe this could be generalized. Maybe inventory iterator would be generalized, and then we would specify that it's of a particular type, or iterating over something of a particular type. But in our case, we actually need to specify this. We actually need to specify the item if we're not using generics, or rather, we need to specify the type of the thing that's returned when we call current. So what are we actually iterating over? Like, what is it a collection of? What's a super type of that? Or what's the shared interface amongst all the things that we're iterating over? And in our case, actually, item maybe makes a lot of sense. So it should perhaps be called game item or something like that, or usable item. Actually, usable is not very strange. Actually, so let's say that instead of thinking of it as a superclass, we could think of it as a capability, as an interface, and then maybe usable would actually make sense. Like it's something that is usable within the game. Anyways, let's actually say that it returns an item. And then these are fine, right? Has next and next, right? Next is just void, it moves the pointer, and has next returns a bool. And then lastly, the concrete iterator, what would this be? Well, unless we have these trivial scenarios with lists that we were talking about before, or recurring data structures, then these would pair one-to-one with the inventories. So if we have a handheld inventory, that means we need a handheld iterator. And that's it. Then we have something which actually kind of looks like a scenario, like an actual usable scenario. So before we wrap this up, let's super quickly just look at some short example code for this particular scenario. So let's start with the inventory. So we've got an interface called inventory, and it essentially just states that to be an inventory, you need to have a method that returns an inventory iterator. And by the way, I now realize that in the previous UML diagram, I forgot to change this piece of the inventory. I said that the contract of the inventory is that it requires a method called getIterator that returns an iterator. But that was of course actually only true in the sort of generic scenario where we called it iterator. But now we actually called the iterator that we put here, we called it inventory iterator. So of course this getIterator method needs to return something of type inventory iterator. So it should return something of type inventory iterator, and it's called getIterator. And then of course I'll put ... here to say that clearly probably our inventory does more things. Anyways, after that we then have concretions. So let's just do a single concretion. So let's say that we have this handheld inventory. So we have a class called handheld. Actually, let's do the full name as we talked about before. Handheld item inventory. And actually now I'm realizing maybe this should be called item inventory rather than inventory, but whatever. So handheld item inventory, and it is, sorry, I opened the class here, but that's not true. We should say, I'm breaking the line here, but implements the interface inventory. Open up the class, and then what does this class do? Well, it needs a specification of this getIterator method. But of course, it also needs to do the stuff that handheld does. And what we said that the handheld does is that it has something in the left hand, it has something in the right hand. So let's just do that. I mean, let's say that there's a property. So maybe there's a public getter. So the type was item, right? What we iterate over is items. So there's a public item called write. I'm using C# like syntax, like the properties syntax of that. So it's a public property write that has a getter, but a private setter. And then we do exactly the same thing for left. Public item, left, property syntax, public getter, private setter. So the point is then that you can, from the outside, if you have a handheld item inventory, you can access what's in the left hand and what's in the right hand. But you can't set these. These have to be set internally. So let's then build a constructor. Let's say that we have a constructor. So public handheld item inventory. Oh my God. And then let me open that up. It takes, so I'll break the line here, but it takes an item, which is what's supposed to be put in the right hand, and then an item, which is what's supposed to be put in the left hand. And those are the arguments of the constructor. Let's open that up. And then what we do is that we simply assign these to the instance variables. So this dot right equals the right that we were passed in, and this dot left equals the left that we were passed in. And then we close the constructor. So we have a constructor here that essentially just takes two items. It takes a right item and it takes a left item, and then assigns these, the right item and the left item, to these instance variables of this particular instance. And that's why we define these two instance variables that can be privately set but publicly gettable. This is, of course, again, specific to this particular handheld item inventory that we're trying to build, and not at all specific to the iterator pattern. It's actually, in some sense, pretty silly that we want to iterate over something that only has two items. But the point is that it lives in a context where we have other inventories that are more in need of actual iterations because they have much more items, and we want to be able to treat this handheld item inventory in the same way that we can treat these larger inventories, such as the backpack inventory. And now we just take this one because it's simpler. But now let's actually build this method, the getIterator method for the handheld item inventory. So what do? We say, okay, public method that returns an inventory iterator. And again, I should have called this inventory item iterator, but whatever. Sorry, I'm being confusing with mixing the different names. But anyways, it's a public method that returns an inventory iterator and is called getIterator. Takes no arguments, and let's open that method up. And what does this do? Well, this is super simple. This just returns a new what? We haven't written this class yet, but we had it in the UML. It was something on the right side. So a new concrete iterator, and this particular concrete iterator happens to be a new handheld item. Let's actually now put item iterator. And to that we pass this. And that's what we talked briefly about before. So this piece now, this is what's really key in regards to the iterator pattern. So the handheld item inventory returns, when we call getIterator, it returns a new handheld item iterator, which is, in other words, an iterator built specifically for iterating instances of handheld item inventories. It's specifically built for this kind of inventory. And when we instantiate it, we pass this. So we pass this instance into that iterator so that the iterator can iterate over this particular instance. But now let's build the classes on the other side. So let me just add like this divider here, and hopefully we have enough space on this side. So first up is the inventory iterator interface. The inventory interface specifies that to be an inventory, you need a method called getIterator that returns an inventory iterator, an iterator for inventories. So now let's specify the interface for iterators for inventories. So it was enough with iterable and iterator. So this is kind of stupid of me to choose another word that starts with an I, but anyways. So we need an interface that's called inventory iterator. And what does that require? Well, to be an inventory iterator, you need to have a method that returns a bool and is called hasNext. So it needs to be able to answer that question. Then it needs to have a void method that simply moves the pointer to the next item. So that's a void method called next. And then the last piece is that we need something that returns an item and is called current, which, if we were to be really exact, should actually probably be called getCurrentItem. Let's close that interface. So let me draw a divider here also for clarity. And let me also actually write that, of course, we need to have an interface for items. I won't specify any implementation for that because that completely depends on what we want items to do. But that's the inventory iterator. But here we said that we have a method called getIterator that, yes, returns an inventory iterator, yes, but this inventory iterator, in this case, happens to be a handheld item iterator. So we now need to build that. So then let's say we have a class called handheld item iterator, which I'm doing a line break, but which implements the interface inventory iterator. So again, I'm being a bit sloppy with the name. Here, the handheld item iterator is an item iterator but here we called it an inventory iterator. So let's actually unify that. This is getting too confusing. So let's decide. I mean, either we call them inventory iterators or item iterators. I mean, they are actually inventory iterators much more than they are item iterators. Yeah, absolutely. Sorry, they should be called inventory iterators. So let's remove this stuff and write the same thing, but this time without the word item and instead with inventory. So we say return new handheld inventory iterator. Sorry, that makes more sense. And then we open that up, and to that we pass this. And then we close that. So again, same thing as before, we're passing this instance to the instantiation or to the constructor of this handheld inventory iterator. And the intention was, of course, that this is the same thing as here. So instead of item here, instead of handheld item iterator, we should have handheld inventory iterator, which makes a lot more sense, right? Because we have inventory iterators and we have a handheld inventory, which this is probably where I started to confuse myself because I call this a handheld item inventory. So probably we should have used item inventory all over, but now, let's let this one be the discrepancy, whatever. Or okay, why am I so sloppy? Let me just fix this. So let's name this handheld inventory. And then we are more consistent, at least. But yeah, I mean, if I was actually at a computer and didn't have to retype with my hand, I would add the word item to all of these to make it more explicit. Anyways, so what's the implementation of this concrete iterator, of this handheld inventory iterator? Well, the job of that is to simply iterate over this handheld inventory that it's been passed when we pass this here. And it needs to do so by using these three methods that are part of the interface of the, or that make up the interface of an inventory iterator, which it implements. So before we can do that, we need to save the reference to this thing that we were passed. In other words, we need to save the reference to the handheld inventory that the handheld inventory iterator was passed. So let's add a constructor. So public, oh my God, handheld inventory iterator. So that's the constructor, and to the constructor we get an argument, and that argument will be of type handheld inventory. So handheld inventory, and let's just call that I. I'm sorry. To stay sane. So that's the inventory, and then we save that. So this dot let's say inventory is equal to this I that we were passed in, and then I'll close the constructor. And then of course we need an instance variable that we save this in, which is this dot inventory. So let's make a private instance variable. Let's assume private is implicit. So let's just say that we have an instance variable of type handheld inventory, and let's call it inventory. And this inventory variable will be assigned with the I that we were passed in through the constructor here. So when we pass this from the inventory into the inventory iterator, then the inventory iterator will save this reference to the inventory that it was passed. Importantly, we should notice that the type here is not inventory, but the concretion. So it is not inventory, but handheld inventory. So it's not the abstract inventory, it's the concrete inventory. The reason for that is that without downcasting, we need to be able to, in the iterator, treat this inventory as a specific handheld inventory. In other words, we need to be able to access the right and the left thing that this handheld inventory exposes. Because if we just treated it as an inventory, we wouldn't have that. I mean, there's nothing about the right and the left in this. We just have get iterator. And then we would have to downcast it, and then that's completely unnecessary because the intention of the handheld inventory iterator is to be used with handheld inventories and not with all inventories. So we couple to that specific class because that's the intention of that. Of course, then, again, as I was saying before about like going further down the hierarchies, of course you can have further hierarchies downwards from the handheld inventory. Or again, like if you don't want to get sort of stuck into this whole taxonomy idea of like constructing these massive chains of objects or massive typologies, these massive class hierarchies, you could, for example, say that the handheld inventory iterator iterates over handheld inventories, and instead of a handheld inventory being a class, it could be an interface of which there are multiple concretions. But this is a different story, and I think you can figure out how to do that. So we have this instance variable that is called inventory and refers to a specific handheld inventory. And in that variable, we've put the value that we were passed in the constructor. Moving on, now we need to have implementations for has next, next, and current. And there are, of course, tons of ways of doing that. I'll just make the assumption that whenever we iterate through it, we first want to have access to what's in the right hand and then to what's in the left hand. So first let's add the method signature. So we need a public method that returns a bool and is called has next. And this has next method should say whether we have something that we haven't iterated over yet. And so when we iterate over this, we first want to have access to the right hand, and then we want to have access to the left hand. But let's assume now that we haven't gotten access to anything, so we should answer true in that case. Let's say that we have an index variable. Let's add another instance variable here. Again, like this is really a concretion, like an implementation detail. You could do this in a multitude of ways, and I'm just going to do it in the way that first came to my mind, and I don't at all claim that this is sort of an elegant way of doing it, but whatever. So let's say that we have this index variable here of type int, and we call it index. And then in this hasNext method, the hasNext method that returns a bool, we simply switch over this index variable. So let's think about it. In the case that this index is 0, we want that to mean that we haven't returned any of the items, which means that we have a next item and the next item will be the right item. If it's 1, let's think about it that way. So actually, instead of an index variable, maybe we should call it returned or something like that. So if you think about it, I mean, the variable corresponds to how many items we've returned. If it's 0, then we have 2 left to return. If it's 1, then we have 1 left to return because we've returned 1. And then if it's 2, that means we have no left to return because we only have 2 items, and 2 minus 2 is 0. And so we've returned 2 items already. But anyways, let's just keep calling it index. So in the case that the index is 0, we should return true. In the case that it's 1, we should return true. And in all other cases, we should return false. So actually, if I think about that, that just means that we can more simply express this as that return index is less than 2, right? Because if it's 0, we have 2 left. If it's 1, we have 1 left. And if it's 2, then we have none left, and then we will return false. So that's the implementation of the hasNext method. Then let's build the next method. So public void next. And that will be super simple. Here we just say this dot index plus equals 1. So we add 1 to the index variable. And actually, to be explicit, let me say this dot index here as well instead of just index. So return this dot index is less than 2. And then let me think about this. Does this actually play out correctly? So this means first we ask hasNext, and then we say yes. But then when we next it, we move the index variable. Right. So that's fine. And then lastly, we have the current method that needs to be implemented. So here we say public item. So this method returns an item, and it should be called current. Takes no arguments, and what's the implementation? Well, I'm running out of space here, so I have to figure out a short implementation. But the thing is that we now need to remember that if we run next, then the index is not, sorry, we didn't give a default value. Maybe this default value should be 0. So we start off at index 0. And so I got a bit stuck here now thinking about this, because if we want to return the current item, we need to remember that the order in which we were doing things before was that we were first asking, do you have another element, like hasNext? And then we were asking the iterator to progress the pointer. In other words, we said next, and then we asked for the current. But actually, if we always start in that, and it's kind of unintuitive, because then the current initially needs to point at something which doesn't exist, like it needs to point at a no index, right? Or we need to return the same item in the 0 index and in the 1 index, which kind of doesn't make any sense. So when I was saying before that we should call first has next, and then current, scrap that. Let's just instead say that we first call has next, then we call current, and then we call next. So we assume that initially the pointer is pointing at the first element, if there is a first element. We ask has next, and then if we has a next, then that means that we have an element there. And then we can call current to get that out, and then we can call next to progress to the next. And yes, yes, I just realized that the naming now is semantically completely stupid. And also I realized why they in this book actually called it is done rather than has next. So instead of has next, the contract is now that there is a method that returns a bool that is called is done. This is going to make tons of more sense. And then instead of this being called has next, we call it is done. There's a method called is done, there's a method called next, and there's a method called current. What we do is that we say, is the iteration done? If it's not done, then we can ask for the current element. And then when we ask for the current element, we can say progress to the next element, and we ask, is the iteration done? In other words, would I get an element if I now call current, or am I only, or is the iteration now done? Makes a lot more sense. I'm sorry about that. Moving on. So the implementation now for the current method will be very simple. If the index is 0, we need to return the right value. If it's 1, we need to return the left value. And in all other cases, we don't have a value to return. So either we need to throw an exception, or we return null, or null object pattern, we return a null item. But that's a different story, and please come back to that thought when we've talked about the null object pattern. It's going to be in another video. So here, let me just make that switch case. So here, let me just do that switch statement again. So switch over this dot index, and in the case that we have 0, then we return, here's the key point, we return this dot inventory dot right. Then we do exactly the same thing, but for the case 1, we return this dot inventory dot, but now we return left. And then finally, the default case. So in all other cases, we simply, because I'm running out of space, let's return null. Close the switch and close the method. And actually I forgot to close this class over here. So I got a little crammed for space, but let's just super quickly recap. So we have 2 polymorphic hierarchies, one here and one here, and then we've stuck this item in between that doesn't really have anything to do with this hierarchy. And the thing is that we have these different inventories that contain items, and these inventories, the concrete inventories, have completely different structures. But there is this requirement that we want to be able to iterate over these inventories. We want to be able to sequentially go through all of the items in the inventory. Again, for a number of different good reasons, hypothetically. Like in our game scenario, it could be because we want to display all of the items on a screen, or we want to simply shift which item is the active item that the player is currently using, or something like this. So that's why we say that to be an inventory, you need to implement the getIterator method. And the getIterator method will return something of type inventory iterator, which we've defined here, inventory iterator. And that is an interface here. And the contract for being an inventory iterator, or for behaving as an inventory iterator, is that you need to be able to do these 3 things. You need to be able to return a bool when I ask is done. And the inventory iterator needs to be able to supply an item when we call the method current. So it has a current item at all times. And then when we call next, it simply shouldn't return anything, but the expectation is that next should simply progress the pointer of the iteration. And then we have concretions of these two abstractions. And the concretion here on the left side is that we have an example concretion of what an inventory might look like in our hypothetical game. So we call this the handheld inventory, which again implements the interface inventory, which then puts the demand on it to implement the method getIterator. So down here we have, let me change the color because this pen is dying. So down here we have the getIterator method. And this getIterator method does something which is specific to the handheld inventory. And in some sense, probably all of the different inventories would look very, very similar in terms of their getIterator methods. But the difference is which concrete iterator they actually return. And in this case, we return a handheld inventory iterator, which we find over here, a handheld inventory iterator. And again, back to the point that this is actually a factory method. So if you want to think more about that interaction, do check out the factory method pattern video again. But so when we call this getIterator method, we get back a handheld inventory iterator. And when we instantiate that handheld inventory iterator, because it's concrete and we build it now, we instantiate it now, then we pass this. So we pass the instance of this handheld inventory to the handheld inventory iterator. In other words, it's kind of like saying, I am a handheld inventory, I instantiate an iterator, and I give the iterator a reference to myself so that it can iterate over me. Right? It's kind of like I ask it to iterate over me instead of me iterating over myself. That's why I'm passing myself to that. And then of course the handheld inventory has a bunch of handheld inventory specific stuff. All of this stuff is handheld inventory specific. Like, what does a handheld inventory actually do? Well, so specifically in our scenario, what it does is that it has a right value and a left value. And when I say value, I actually should have said items. So the handheld inventory has a right item and it has a left item. So we're modeling the inventory of what you hold in your hand. So you can hold something in the right hand and you can hold something in the left hand in this game. And these two properties are publicly gettable but privately settable. So we set these values in the constructor when we construct this handheld inventory, but you can access them publicly from the outside, which is what we will take advantage of now that we're passing this, now that we're passing ourselves, now that we're passing the handheld inventory to the handheld inventory iterator. So over in the handheld inventory iterator, what we've specified is that it implements the interface inventory iterator. So it behaves as an inventory iterator. And that puts the three demands upon us that we mentioned before. We now need to specify implementations for the three methods is done, next, and current. And these we have down here, is done, next, and current. And essentially, what we do is that is done checks whether we have iterated through the right element and the left element. Next progresses some kind of index counter, some kind of pointer, so that we can keep track of which ones we have showed. And then current gives us the current element that we are currently at. But before we get to that point, what we need is that we, in this constructor here, in this constructor of the handheld inventory iterator, as we said down over here in the handheld inventory, the handheld inventory, when it instantiates a handheld inventory iterator, then it passes itself, right? It passes itself to that constructor. And that we can see over here. I'm sorry for all the line breaks, but so we have a constructor called handheld inventory iterator, and as an argument to that, we're passing something of type handheld inventory, and we call it I here. And then the key point is that we take that I and assign it to this dot inventory. So an instance variable called inventory that we've specified here, handheld inventory called inventory. So an instance variable of type handheld inventory, which is called inventory. And again, specifically the type handheld inventory, not inventory, but specifically the concrete type handheld inventory, because we need to be able to access the handheld specific stuff and not just the inventory stuff, because now we need to be able to access left and right, which, as we said, we need to use these public getters to access these items. So now now getting to the is done, the next, and the current, what we then do is that we make use of this inventory variable that we have, but we also make use of this index variable that we create in order to keep track of where we are. So this pointer or this cursor that points to where we are at in this iteration. So the implementation of the is done method is simply that we say that, okay, if the index is less than 2, then that means that we haven't seen all the items yet, or we haven't provided all of the items yet. We haven't iterated through all of the items yet. And then when we say next, we simply increment that index. We add 1 to that index, so that when this index, according to the is done method, gets to 2 or larger, then that means that we are done. We have nothing more to iterate over. In a real application, maybe you would set this so that if it's larger than 2, you would set it to 2 so that you could not next it up to a very high number in case you also want to have a previous and not just a next. But I'm sure you can figure that out on your own. And then lastly, we have this current method, which simply returns the item that we are currently at. And again, we were saying that we use this index variable in order to keep track of which item we are currently at. So then we simply here do a switch statement. Again, like there are probably much more elegant solutions to this. I'm just using a solution that works now. So we do a switch statement over this .index. And if this .index is 0, then we return the right one. If it's 1, then we return the left one. And in all other cases, we simply return null. So that means that initially, first time we call current, we'll get the right one. Then we'll, as soon as someone call next, and then call current, we'll get the left one. And then if someone calls next again, then we'll be outside of the iteration, and then we will simply get null. So that's it. Let me just do this. Oh my god, I'm not sure if let me do this. Let me flip the whiteboard. The way we can now use this is that we build an inventory. So let's say that when I have a variable containing an inventory, let's call that I, and in that inventory, I'll put a new handheld inventory. And then I'll just put ... here to avoid having to write that part. But as you saw on the other side, when we instantiate the handheld inventory, we need to supply an item to the left side and one to the right side. But let's not care about that now. So then we have the inventory. What we then can do is that we can extract the iterator from this inventory. So we can say that I want to have an inventory iterator, and let me call that iter, sorry for the silly names, and that is equal to the inventory, which I called I, dot, so sorry, let me at least call it inv. So the inventory is called inv dot get iterator. So now I'm extracting the iterator. I'm asking for the iterator from the handheld inventory. And I'll get an iterator which is of the sort of quotation marks abstract type inventory iterator. But concretely, I happen to know, because we wrote the code, that we will not get just any old abstract inventory iterator. We will get a handheld inventory iterator. So something that is capable of iterating over a handheld inventory. And what we can do with this then is that we can say while iter dot is done, and then we need to negate that. So while the iteration is not done, do what? Extract the item. So iter dot current, extract the current item, and then do something with it. Do something cool. So do something cool with the current item, and then iter dot next. And then we close the while loop. So suddenly we can now iterate over the contents of the inventory, or more specifically over the contents of the handheld inventory. And we can do so in a polymorphic manner. We can do so without thinking about whether it happens to be a handheld inventory or something else. If you think about it, if you remove everything above here, or if you just ignore the first line, everything below that is super abstract. This is the interface, and these methods are all part of the interface. So you would get an item back here when you say current. So item equals the current item. So that's on the abstract plane. The inventory iterator is on the abstract plane, and these methods next and current and is done are all part of the inventory iterator. And here when we say actually everything apart from this, right, is abstract, because here we're also saying that we have an inventory. And so that's the key point, so that this handheld inventory may show up from anywhere. So you could take this portion, Everything but that portion that we said is specific, put that in a method, and that's general. That you can do for any old inventory. So this can be put in a method that accepts an inventory, and then you can simply do all of that stuff to the inventory, which means that, again, if you wanted to do a display that displays what's in the handheld inventory, what's in the backpack inventory, and what's in the home inventory, you only had to write that code once, and then you just accept a different inventory. Whew. I don't know how I try to make these short videos and then I end up with super long videos. Maybe I need to learn to not go off on tangents. Anyways, if you've stuck around to this point, thank you super much for watching. Without you, this channel would not be a channel. If you have any questions or comments or things that you want to talk about, shoot it in the comments and let's talk about it. Links to these books are in the description. I hope that you now feel that you have a better grasp of the Iterator pattern. Remember to subscribe for more videos like this, and feel absolutely free to share any of these videos with anybody who you think might appreciate it. Massively appreciated from my side. Again, thank you super much for watching, and I will see you in the next one.